Understanding algorithmic complexity through real-world applications in today's fast-paced software development landscape. Mastering algorithmic complexity is crucial for building efficient systems that can handle massive datasets without compromising performance. Whether you're optimizing search algorithms for e-commerce platforms or designing recommendation engines for social media networks, understanding time and space complexity enables engineers to make informed decisions at every stage of system design. The fundamentals of time complexity analysis. Time complexity quantifies how an algorithm's execution time grows relative to input size n. This metric helps us compare different approaches before implementing any solution. Big O notation serves as the standard framework for expressing time complexity. It focuses on worst-case scenarios by ignoring constant factors and lower-order terms. For example, an algorithm with O(n) time complexity will execute proportionally faster than one with O(n) superscript 2 when handling larger inputs. While Big O provides essential insight, other notations like omega, and theta, offer additional perspectives on average and best-case scenarios. Evaluating space complexity requirements. Space complexity measures the amount of memory an algorithm consumes during its execution. This includes both auxiliary space and input storage requirements. When analyzing space complexity, we consider two primary components: the memory required to store input data and any extra memory used for computation. Some algorithms may require significant auxiliary space, which can be critical in environments with limited memory resources. O(1) space algorithms use only a fixed amount of memory regardless of input size. O(n) space algorithms require memory proportional to the size of the input data. O(log n) space complexity often indicates recursive algorithms using stack frames efficiently. Common complexity classes explained. Familiarizing yourself with common complexity classes allows you to quickly identify optimal solutions for various problems. Constant time operations, O(1), are ideal for tasks where access time doesn't depend on dataset size, such as array indexing. Logarithmic complexity, O(log n), typically appears in divide-and-conquer strategies like binary search implementations. Linear complexity, O(n), is expected when processing each element of a dataset sequentially. Square complexity, O(n) superscript 2, commonly arises from nested loops, making it unsuitable for large-scale applications. Exponential complexity, O(2 to the power of n), usually signals brute force approaches that become impractical even for moderate input sizes. Factorial complexity, O(n), is rarely encountered but represents extremely inefficient algorithms in combinatorics problems. Analyzing algorithm efficiency through examples. Let's examine some practical examples to illustrate how different complexities impact real-world performance. Consider sorting algorithms. Bubble sort has O(n) superscript 2 time complexity while merge sort maintains O(n) log n efficiency. In practice, these differences become dramatic with large datasets. Sorting 1,000,000 items would take significantly longer with bubble sort compared to merge sort. For searching algorithms, binary search offers O(log n) time complexity versus linear searches O(n), making it much more effective for ordered lists. These examples highlight why choosing the right algorithm based on complexity analysis can save substantial computational resources. Mastering recursion through complexity awareness. Recursion introduces new considerations when evaluating algorithm complexity due to its inherent call stack usage. A simple factorial function demonstrates linear recursion depth but executes in O(n) time with O(n) space complexity. Tail recursion optimizations can help reduce space complexity in certain languages, though support varies across programming paradigms. Divide-and-conquer algorithms like quicksort showcase logarithmic recursion depths but have varying average cases depending on pivot selection. Properly managing recursion ensures we don't exceed stack limits while maintaining acceptable time complexity bounds. Complexity trade-offs in data structures. Data structure choices often involve careful trade-offs between time and space complexity requirements. Linked lists provide O(1) insertion times but O(n) lookup costs, while arrays allow O(1) lookups at the expense of O(n) insertions. BSTs, binary search trees, balance between search and insertion efficiencies but require careful balancing techniques to maintain optimal performance. Hash tables achieve near constant time complexity for searches, inserts, and deletes under ideal load factor conditions. Choosing the right data structure depends heavily on workload characteristics and expected query patterns. Efficient cache utilization also plays a role in overall performance beyond pure mathematical complexity metrics. Optimizing algorithms using amortized analysis helps evaluate algorithms with fluctuating performance over time rather than focusing solely on worst-case scenarios. This approach becomes particularly useful for dynamic data structures like hash maps and balanced trees. Doubling arrays strategy exemplifies amortized O(1) complexity despite occasional expensive resizing operations. By averaging out occasional high-cost operations over many low-cost ones, we get a clearer picture of typical performance. Understanding amortization helps avoid being misled by rare worst-case scenarios in everyday application contexts. Empirical validation of theoretical complexities. Theoretical complexity estimates should always be validated through empirical testing with actual implementations. Benchmarking against various input sizes reveals whether theoretical predictions align with real-world behavior. Profiling tools help identify bottlenecks that might suggest alternative implementation strategies. Combining asymptotic analysis with practical measurements leads to more robust algorithm designs. Remember that constants matter in real implementations even if they're ignored in big O notation. Testing edge cases separately ensures your implementation handles all possible scenarios correctly. The role of pre-processing in improving complexity. Pre-processing steps can sometimes transform higher complexity algorithms into lower complexity alternatives. Sorting input data upfront can enable faster querying later, especially for range-based searches. Parsing complex input formats once instead of repeatedly improves long-term efficiency. Caching frequently accessed results avoids redundant computations across multiple requests. Strategic pre-processing transforms raw data into optimized structures suitable for rapid manipulation. However, pre-processing requires memory allocation that must be considered alongside time complexity improvements. Concurrency considerations in modern systems' multi-threaded environments introduce new dimensions to algorithm complexity analysis. Parallelism potential varies greatly depending on problem decomposition possibilities. Shared memory concurrency creates challenges related to synchronization overheads. Lock-free algorithms present promising alternatives but come with their own set of challenges. Assessing thread safety impacts the choice of appropriate data structures and algorithms. Modern hardware trends favor parallel processing capabilities, necessitating updated complexity evaluation frameworks. Future directions in algorithm optimization. Ongoing research continues to push boundaries in creating more efficient algorithms through novel methodologies. Quantum computing promises revolutionary changes in complexity classes for certain types of problems. Approximate algorithms provide viable options when exact solutions aren't strictly necessary. Machine learning approaches show promise in automatically finding optimization opportunities within codebases. Hardware advancements continue influencing what constitutes efficient algorithm design practices. Staying current with emerging technologies ensures continued relevance in algorithmic problem solving. Conclusion: grasping algorithm complexity fundamentals equips developers to make better engineering decisions across diverse project landscapes. Effective use of complexity analysis prevents costly mistakes by identifying potentially problematic scaling issues early. Continuously refining analytical skills keeps professionals competitive in rapidly evolving technological environments. Apply these principles systematically to ensure your solutions remain scalable and performant as demands increase over time.